Nice to meet you. I'm Kyohei Mukaida from Tech as introduced, and I'm happy to be the first speaker of this workshop. So my talk will be Blackboard, and please interrupt me whenever you have questions. And okay, my topic would be baryon symmetry, the relation between baryon asymmetry and flavor asymmetry. I think. And this talk is based on two papers, basically. I guess give you a number of archives. Is it loud enough? Can you see?
Yeah.
Okay. And my talk is based on the collaboration with my friends in Japan, Masaki and Kyohei, and also my friends in Europe, Kai Schmidt and Baryon. Okay, and before going to discuss about the relation between the baryon asymmetry and lepton flavor asymmetry, but let me just briefly remind you that there's a famous relation between the baryon asymmetry and total lepton asymmetry. It is probably well known for you. Yep. So as you all know, we have there is a very important observation of consequences that we have the universe has the tiny baryon asymmetry, which is characterized by the baryon to photon ratio, denoted by eta, which is given like baryon number density minus anti-baryon number density divided by photon number density, which is the field of 10 to the 10 from EMB and BB. So the question is how to explain this, because we cannot put them at the initial condition because we have inflation dilute everything. So we have to generate this after inflation, and that is the problem of the baryon asymmetry of the universe. So we know that the baryon asymmetry is there in the universe, but how about lepton asymmetry? And because of the observation or discovery, the theoretical discovery of the spiral, we know that there is a tight relation between the lepton asymmetry, or strictly speaking, total lepton asymmetry, and the baryon asymmetry by the electrolytic spiral. That I will explain next. So, spiral. So, standard model has classical symmetry, accidental symmetry of the global human beam and a cell, and single cell, and times lepton flavor symmetry of LE minus L mu, and still on. So this one is broken by the APG anomaly. So it means that the total derivative of B plus L current is like this. Okay, too basic, but WWL minus B. So I just dropped the indices because it's anomaly. Yeah. So B is the U1 hyper gauge field, and W is its x2 weak gauge field, and they are topological terms. And typically, we neglect this term because for U1 gauge field theory, we don't have any non-trivial vacuum structures. But however, for non-abundant gauge field theory, we have classically non-equivalent vacuum like this. All of you know that. That's for sure. That's the discussion. Something. And the important thing is that this topological operator, since this is topological, means that you can write down this operator as a total derivative of something, which is sometimes referred to as Chern-Simons parental number. For the W means that this is for SU2 and GS, the Chern-Simons. And right, so this is the well-known schematic figure for this number. So if you're going from 0 Chern-Simons number to this 1 Chern-Simons number, then you're generating how many balls? 3 times 3, 3 color DOF, and the flavor DOF, 3 times 3, 9 quarks, and 3 lepton simultaneously. So this is the DOF for the quark doublet. So we have 3 color DOF and 3 flavor for the quarks, left-handed quarks, and this is the DOF for the left-handed lepton. So you are generating 9 quarks and 3 leptons. So you can see that you can generate the leptons. And also, if you have, for instance, starting from anti-lepton, if you have anti-leptons, then by using this process, you can erase the lepton while you can generate the baryon. So in this way, you can generate the baryon from the lepton asymmetry. So it means that the total lepton asymmetry should be also of this order. I mean, you cannot have huge lepton asymmetry, then you overproduce the baryon asymmetry. Yeah. Okay. But important thing is that this is tunneling process. So at the current universe, since we are there, the baryon should be approximately conserved, and this is guaranteed in the standard model because this is the tunneling aspect. But at high temperature, you have thermal fluctuation. The thermal fluctuation can easily overcome this potential barrier, which is the mass of the spiral configuration. And this becomes super efficient when the temperature becomes greater than, say, I don't know, 100 something GeV around electrolytic temperature. So this is the schematic figure. So 0 electric phase transition, Q1B minus V plus L is approximately conserved, but however, above this is broken efficiently because of the huge thermal energy. Okay, then given this, so then the next question is, what is the chemical equilibrium? So I said that you can generate the lepton asymmetry from the baryon asymmetry from the primordial lepton asymmetry, but so how much? So that is the also well-known thing. But let me just briefly explain the idea how to compute this. How you can generate the baryon asymmetry from the lepton asymmetry. Or more strictly speaking, B-cell asymmetry generate the baryon asymmetry from the primordial B-cell asymmetry. Okay, so the base typically what we do is to just employ the ideal gas approximation. Ideal gas approximation is just saying that all the standard model particle at the leading order just behaves as a free particle, relativistic free particles. So it means that your phase space distribution of some particle with species I denotes the species of the standard model. And as you know, for relativistic particle, it will be very small. Maybe you know that it's given either Bose distribution or film distribution. Minus sign for Bose, boson, and plus sign for Feldman. So this is the phase space distribution of free particles, relativistic free particles. And if you use this approximation, then you can compute the asymmetry. I introduced mu I, which is an important parameter. This is the chemical potential for some species I. So it means that if you have non-vanishing mu right-handed electron, so you are having more right-handed electron than anti-right-handed electron. Okay. So in the presence of this chemical potential, you can compute the asymmetry. Asymmetry is defined by number density of some particle I minus number density of antiparticle I, and which is just given like this, as you know. This is for Baryon, actually. And this is for boson. GI denotes the multiplicity and not the degree of freedom. So for right-hand lepton, this is 1. For left-hand lepton, this is 2. And there's a tiny difference between whether this particle is boson or not, or fermion, but well, basically it's just given like mu times t squared. Here I assume mu over t is much smaller than unity, because we have correction, for instance, cubic power of mu, but I just dropped it because typical mu over t we need to explain this tiny baryon asymmetry. It's super small, so you can just use in the function. Okay, so that is I think, typical assumption people employ in order to understand how this baryon asymmetry is generated from mathematics.
Can I ask you, is there any measurement of the lepton asymmetry?
Which one?
If there's any measurement, I'm asking on the lepton asymmetry.
This one.
Equivalent to the measurement of the baryon asymmetry.
If you have total lepton asymmetry, I think, yes.
No, neutrinos, right?
Neutrino.
There is no measurement.
There's no measurement. I mean, neutrino. Okay. If you don't talk about the primordial lepton asymmetry, I mean, for instance, if you have lepton, of course, we can have lepton asymmetry after electric phase transition. In this case, we cannot apply this. I mean, conversion. So in that sense, that is asymmetry for neutrino, and I think the tightest bound is coming from BBN. But it's super weak. I think the chemical potential should be smaller than 0.0 something, if I remember correctly. For the electron neutrino.
This is in BBN. This is coming from where? What's the field?
I don't want to go to that direction, but I can show you the reference afterwards.
Okay.
But anyway, what I want to say here is that if you have primordial lepton asymmetry, and if it is too huge, then you will overproduce the baryon. When did I start?
Quarter past, I think.
Okay. A bit speed up. Okay, then all I have to do is just impose the relation between the chemical potential and standard model interaction. Maybe it's probably it's too basic, so I just skip. But for instance, for the electric started on, it should be like this. 3 from parallel F, and QF is this mu QF. Mu of QF is the chemical potential for the quark doublet of flavor X.
I'm calling? Yes. Oh, my calling. It's really close. Yes. Calling. What? Yeah.
And you have many interactions like strong Baryon, Yukawa. I don't write them all because I think you can find it in any review or any textbook or whatever. So I don't write everything, but we can. It's essentially what I want to say here is that assuming that these kind of standard model interactions are efficient in their universe, that relates this chemical potential in a non-trivial ways, and also we have some conservation laws. So we have conserved charge like U1 hyper, U1 L, and LE minus L mu as I said, and L mu minus L tau. But this one is the gauge charge, so it should be neutral. And we impose neutrality condition, and then the result should be expressed as the function of this conserved charge. Yeah. So the basic well-known result of this conversion factor is given like this. So QB is given like, I skip all the details. Okay. So sorry, small QB is the asymmetry defined by the number density of baryon minus anti-baryon. and the same way for the QB itself. So this means that you have primordial lepton asymmetry before the electron weak condition occurs, then you can generate the baryon asymmetry with this conversion factor. Probably all of you know that.
Remind me, that includes so that's in the electroweak phase transition, just taking into account the electroweak phase.
No, before the electroweak phase transition. Yeah, so
yeah, okay. So it's not including the washout effect or anything like that.
No. It's like okay. This value is just the conversion factor.
Right. Yeah.
When the baryon is super efficient.
Yeah.
So if you not precisely compute this, then you have to extract the electroweak crossover. Then this will give you more precise. Yeah. Okay. Then so it means that you have to generate this before under GB, and well-known model would be the, for instance, leptogenesis. I'm not explaining the model here today.
The Q is the charge.
Sorry. So Q is the charge, and okay, any charge I will write down is defined by number density of some I minus number density of anti I.
Just charge density.
Yes, it's the charge density. Sorry, charge density. Small q is charge density. I'm sorry. Large q, okay. Large q is for charge. Okay. So then I will move on to the main topic about the relation between the baryon symmetry and the lepton flavor symmetry. Here, up to now, I just discussed about the total lepton symmetry, but I don't discuss the lepton. Total lepton symmetry, but I don't discuss the lepton flavor symmetry. Yeah. But you might think that if you given this result, it does not depend on Q, LE, mu, or mu itself, right? So you might think that the primordial lepton asymmetry does not generate the baryon symmetry. But this is actually not the case. So let me just start with the first opportunity to generate the baryon symmetry. So actually there are two. One is related to, sorry, I have to just wait, but about the ideal gas approximation. And another one is related to the negligence of the PV human hyperchance emissions. So, yeah, so let me just go into the first opportunity, which is the correction, which is coming from the corrections to the ideal gas approximation. So that is a well-known result. But the reason why it does not depend on the lepton flavor symmetry at all is actually coming from the assumption of ideal gas approximation. So once you assume ideal gas approximation, then you're essentially neglecting all the interactions. So if you neglect the interactions, there is no difference between the flavors. So it should be the case. Well, you should expect that the result does not depend on the lepton flavor symmetry because there's no way to distinguish different flavors. So it means that if you want to see this relation, you have to take into account the corrections to the ideal gas approximation. So it means that we have to consider MLO right corrections from lepton results. Okay, a bit abstract, but I want to say is that something like this is the reading order terms for fermion, for instance. Right. So this is the reading order term. But there should be some correction coming from lepton recall. So we have to take this effect into account in the calculation. Okay. I want to explain how to calculate this. So it's difficult to explain within this 45 minutes. But the basic idea is to just compute the grand canonical ensemble at the next reading order. Then the charge should be given like derivative of some partition function of the grand canonical ensemble. And if you compute this grand canonical, partition function or log of partition function at the next leading order level, then you can systematically take this effect into account. Then by using the formalism, you can also compute this effect of the lepton Yukawa. Okay. But I just write the result without the explanation. Okay. So result would be something like this. Reading order first. Subtraction proportional to total bit given the asymmetry plus complicated function.
So I'm just confused with what's going on. So at high temperature, well above the weight scale, any flavor effect should be suppressed by mw squared over t squared, right? Just because the flavor changing ongoing all the time.
Yes, ongoing all the time, right?
So this whole effect is not just Yukawa suppressed; it's also mw squared over t squared. Is that correct?
No, it's just suppressed by Yukawa. I
guess I'm confused because there's I mean the flavors are at equilibrium.
Yeah, flavors are equilibrium, right?
So how can the flavor asymmetry have any significance? It's their own.
Right. For instance, if you look at the one loop of the fraction to some Baryon propagator, then it depends on Yukawa, right? So for instance, thermal mass depends on the Yukawa coupling.
But the number density is equal. But the number densities are equilibrated at high temperature.
Yes, it's equivalent. So I already assumed that all the relation between the chemical potential, but still, if this expression is different, then you see that you find the difference in the final result. I'm just saying that the relation between the chemical potential and the charge density is different. But however,
sorry, the charges are equilibrated, no? The net charges. But what you're saying is that there is the thermal masses have a weak dependence on the Yukawas.
Yeah.
But why
and this changes?
This changes the calculation of, for instance, charge density because this is basically given by the integration of some phase space density on pole, and that is modified. Well, this is already ideal gas approximation. You have to properly define this concept, but.
Yeah, I'm very confused. I mean, if we turn off, you're saying that if we turn off chemical potential for whatever reason, the zero chemical potential will still be an asymmetry. That's what you're saying here?
No. Zero chemical. Sorry. This also should depend on chemical potential.
Okay. And is the chemical potential of the given flavor? I know is the flavor.
Mm-hmm.
And so I guess that's again confused. Suppose that for one flavor the chemical potential is 0.
Mm-hmm.
You're saying there would still be an asymmetry, even though I have a fast conversion to that flavor, and then given that flavor has a 0 chemical potential, I can convert also to the antiparticle. So I don't understand how you gain an overall asymmetry in the limit of even one chemical potential vanishing.
Even one chemical potential vanishing. I mean, here I just write down the charge density for given chemical potential mu I. But however, after this, you have to put all the constraints coming from the efficient conversion of the, for instance, if you have
of the flavors,
of course, flavors.
I see. So here, this is assuming this. You're not writing the equilibrium solution. You're just this is in the limit of no communication between each flavor.
Yeah.
I see.
Yeah. Sorry, maybe can I ask you something more? So the idea is that you have the sphalerons relating B minus L to B, and now Q B minus L will depend on the flavor through this small effect.
Yeah.
Then
I will write down the equation.
But at high temperature, all of these chemical potential for all flavors are going to be the same.
Yeah.
The different chemical potential for the different flavors will be the same just because they're in equilibrium.
No. For lepton flavor is not in equilibrium because the standard model has the lepton flavors. I mean, in the standard model, lepton flavor is a good symmetry, right? It depends on how you implement the neutrino. I mean, what I'm saying is that just
neutrino density.
This one is on top, discharged. Baryon, all the flavors should be the same, but for the lepton, each lepton flavor has to could have different asymmetry. Yeah, of course, if you have some specific models with neutrino, then maybe this lepton flavor should be also in equilibrium, but yeah, I don't discuss it.
Well, I mean, the point is that you're breaking the symmetry with the electroweak symmetry breaking. So that's why I was asking whether it's suppressed by MW squared over T squared. Because at low temperature, you don't have this U1 cube.
Right? Yeah, that's right.
You have just the U1L.
Yeah.
And so you are changing. You can at any temperature you can always change the flavor and through the W, and it just suppressed. This whole process should be suppressed by MW.
At the low temperature, because of the neutrino mass, there is no lepton flavor. I mean, lepton flavor is not a good symmetry, and they are just equilibrated by the neutrino oscillation. Okay, so let me write down. I'm not sure it has some information. Let me just write down. So a super complicated function. Y tau square Q L mu minus L minus L mu plus 2 that and I neglect the conversion factor coming from the electron equal because that is too small. Okay, so this is the result in explain. So this is the reading order. We also have the correction to the conversion of the beam, total beam as L to the Baryon symmetry, but this is too small, so we can just neglect. This one is the new one. Very complicated factor, but this is of the order of, I forget, some 0.43 or something. And this X, okay. I should be self-consistent, but I'm sorry. I'm not consistent, but now I'm taking into account the effect of Baryon deduction. But X is a function of phi divided by T, and XSP means that I just evaluated this phi or Higgs divided by temperature when this Baryon is decoupled from the function because of the exponential progression. So it's of the order of. If I insert this expression here and there, then I get this number. Okay. So you can see that from this, the contribution proportional to lepton Yukawa squared, the lepton flavor symmetry can contribute to the total Baryon symmetry. And the big result is known in by Riley and Shaposhinsky. Almost 20 years ago. Now from this, of course, you can estimate the Yale parameter or yield parameter of Baryon, which is defined by the UV divided by the entropy density. So you get something like this. LU minus L. I just normalize so that to give the correctly color here. Okay, so there are two contributions. I think, and this one is actually typically dominating. You have if you don't have the cancellation between this LE minus LU plus 2 times LE minus L plus. So this means that if you like to explain this baryon asymmetry by this mechanism, then you need the asymmetry in this particular combination of the order of 10 to minus 4. So this is much larger than the usual mechanism of generating the total baryon asymmetry, baryon asymmetry from total lepton asymmetry, because all you need is just the total lepton asymmetry of the order of 10 to minus 9. But here, if you want to explain baryon asymmetry from this mechanism without B-manifold asymmetry at all, then you need a bit large asymmetry, and that is the result. So you can see that even the lepton flavor symmetry can generate the total baryon symmetry. Okay. Any questions? Fine.
I have a question. So is this the primordial asymmetry or the one you would measure in the lab today?
Sorry, this is the primordial one. So, okay. So in order to have this environment, the spiral should be equilibrium. So we need this asymmetry before electric phase transition. So it's primordial. And as asked, so the question, yeah, right. So after electric phase transition, we have neutrino oscillation, and at that time the flavor asymmetry is going to equilibrate it by the neutrino oscillation.
Can you make a connection between the two?
Primordial one and the current one. Mm-hmm. In principle, yes, but I don't know how to do it. I mean, if you solve this BBN in the presence of this large lepton flavor asymmetry, and maybe we can, I don't know, we can discuss whether or not you have some effect on the BBN. But typically, I think no.
Isn't the statement that play times from zeroth order, the flavor is just 111, even though we start with the right? I mean, as they propagate, you expect the 111 reaction.
Unless you measure it at BBN.
But at the BBN, and we have neutrino oscillation. So
yeah.
But if you have some non-equilibrium non-equilibrium effect at the BBN together with neutrino oscillation, maybe there is some remnant, but I think we need some numerical studies. I think actually there are some papers to stuff like this, but I can show you interested. Okay. So this is the pathway to generate the lepton flavor symmetry to the baryon symmetry. So another one is the chemical U1 hyper. So up to now, although the total baryon asymmetry is I just talk about the effect coming from this one. Because typically, this doesn't contribute at ground state because the U1 theory does not have non-trivial Baryon structure. But if you allow non-equilibrium situation, this can contribute. And that is the effect. I'm going to talk about the effect of this term. So it is known that if you have chiral asymmetry, then there is an instability in one polarization of U1 hyper or any gauge field activity. But the Abelian one is more important because magnetic flux cannot be cut for the Abelian gauge field theory. So the magnetic flux is a good IR variable. It means that if you have instability, actually, as we can show that the expectation value of BB dual becomes non-zero, then you are changing the Baryon asymmetry. It's totally different. So the question is how this lepton flavor symmetry is connected to this, the instability of the given gauge, given hypergauge field. So in order to understand this, we have to introduce some concept. It's known as chiral Cosmology instability. So important fact is that in the presence of chiral symmetry, the standard model is the chiral theory. So if you put any chemical potential to the standard model, this is the universal chiral symmetry in some sense. And the important thing is that this current, which couples to this given hypergauge field at low energy or at low frequency or low energy scale, this current should be given like this. This is the ordinary Ohm's law, you know. This is the electric conductivity, and probably we all know that if you apply electric field, then the current is proportional to this electric field. But if you have chemical potential acting due to the chiral asymmetry, here I denote this chemical potential for you hyper as mu subscript y 5. And this is proportional to CP. This is allowed because chemical potential is the CP operator, so this is consistent with the CP transformation of the current. But if you don't have chiral symmetry, then you don't have current that is proportional to BP. And this effect is known as chiral magnetic effect. And this is very important. So if you have Pfister, you have
mu is like proportional to the thermal mass of the beacon. Is that what's going to happen? Where is the chemical potential coming from? It's just some thermal plasma.
This mu is actually a linear combination of the chemical potential of the standard model. And the B field does not, well.
Is it proportional to the density?
No, it's just proportional to the chemical potential of the standard model. So it's, I see.
So why is there a chemical potential for B which is massless?
Because B field, magnetic field cannot cut. So it means that the long wavelength magnetic field cannot be screened within the standard model. So because we don't have monopole. So that is the crucial difference of the U1 gauge field and non-Abelian gauge field theory. Non-Abelian gauge field theory, we can have master for the static magnetic color magnetic configuration because we can cut them. But however, in the U1 theory, we cannot cut it. So the magnetic flux is a good low energy, well, it's non-equilibrium, but a non-equilibrium variable. And that's why the low energy effective theory of QED in non-equilibrium should be MHT, right? So we have magnetic field. Of course, electric field is spinning, but the magnetic field is moving around. And for this reason, this is not the thermal mass of the magnetic field, but still we have some effect coming from the symmetry that I will talk about.
At some point you generate that at the electroweak precision, I imagine.
Electroweak?
How do you generate electroweak?
This one? Which one?
Magnetic field, which is...
This one?
Mm-hmm.
Yeah, I will talk about it. Yeah. The magnetic field is actually generated from instability. That's what I talk about. But okay, let me just write down this. First, this is MHD. MHD, which is, I mean, the electric field is not dynamical because it's screened. If you insert this current expression into the Maxwell equation, then essentially you get this kind of equation.
So these are large scale coherent magnetic fields, or can you, it doesn't matter?
I will explain. It's not yet fixed. I'm just writing down some equations. So if you're going to the UV, I mean then you can essentially neglect the effect of the presence of the thermal plasma. But still, mu5 is there. Then still you find some instability. But anyway, so let me just proceed. Sorry, alpha y is the Funny structure constant of given hyperpage here. Rotation. So no, should be proportional to mu right? Rotation factor will be. So if you don't have mu here, we just have diffusion. So any configuration will be diffused at with some finite time, then we don't see any non-trivial configuration of a magnetic field, and you get the system which arrives at the equilibrium, global thermal equilibrium. But if you have this term, that is proportional to mu of 5 times. I should have written. It would be nice. I think it would be convenient to go to decompose this B field in terms of two circular polarization. So we have rotation here, and then you get like this. K is the momentum. K minus plus. Complicated. Something that is essentially proportional to mu by 5, and d plus minus d by 5. Okay. Now it's clear. So if you have positive mu by 5, then the one polarization, flat polarization, becomes exponentially enhanced if this momentum is smaller than this one. So if you have opposite chemical potential mu by 5, then the minus mode becomes enhanced if the momentum is smaller than that one. So that is the instability I discussed. Okay. Now the question is, what is mu plus mu by 5? Okay. I haven't defined it, but just define it. Mu by 5 is given by the linear combination of the chemical potential of the standard model. So epsilon I is this is plus for right-handed Baryon and minus for left-handed Baryon. And GI is the multiplication factor DOM, and YI is the charge of the U1 hypercharge of each standard model particle for the right-handed electron. This is 1, and for the left-handed lepton, this is 1/4. And MUI is the chemical potential acting on some species atom. So you can see that this is, roughly speaking, proportional to the chemical potential of the standard in the plasma. So now you can anticipate that if you have primordial lepton asymmetry and you have non-vanishing mu here, then maybe you have non-vanishing MUI5 here, then you can generate the large magnetic field or by using this instability. But how does lepton frame asymmetry affect MUI5? That is the last version I have to discuss. But if the temperature is smaller than 10 to the 5 GeV, the 10 to the 5 GeV is a kind of special temperature for the standard model, because below this temperature, electron Yukawa becomes fast enough to catch up the expansion of the universe, and all the standard model interactions are in equilibrium below this temperature. But above this temperature, electron Yukawa is decoupled or cannot catch up the expansion of the universe. So that is the reason that this number is important. And if T is the temperature is smaller than this value, then all the standard model interactions are essentially in equilibrium. And in this case, the gauge field does not feel primordial lepton flavor asymmetry because by construction, U1 hypergauge field is flavor blind, right? So they don't see the difference in the flavor. So, and if all the standard model interaction is also in an equilibrium, then again, in equilibrium at the leading order, there is no difference. So intuitively, you should expect there is no effect at this temperature. But above this temperature, right-hand electron is not in equilibrium. Then there is a non-vanishing contribution to mu right. Like, again, complicated. Maybe that number is not important, but the complicated factor mu e minus some factor and essentially proportional to primordial lepton flavor asymmetry. So since we have this number, then we have instability, and you are generating some large scale magnetic field in the outer universe. And what happens if they get generated? And you can infer the effect by just looking at the current equation of right-handed electron, because at this temperature, electron Yukawa is not in equilibrium. So the right-hand electron is just broken by BB dual, because we don't have Yukawa. So if you don't have, if you don't generate non-vanishing expectation value of BB dual, right-handed electron is an approximately conserved quantity at the temperature. But however, if you generate non-vanishing BB dual, you are changing the number of this right-handed electron asymmetry. And indeed, you can see that at equilibrium, if the mu y5 becomes smaller and smaller by changing this mu e to cancel out the contribution coming from this lepton flavor asymmetry, so that this becomes zero, then we don't, that instability stops, and that's the end of this production mechanism. So this determines the primordial asymmetry carried in the electron sector. By requiring this to be zero, then your mu e is essentially proportional to some complicated factor and electron flavor asymmetry, E minus L mu, and also L mu minus L pi. So if this is achieved, then this production stops. And actually this since BB dual is also total derivative of something, which is sometimes we refer to as the helicity charge or whatever. And if you know the final value of the electron, right-handed electron charge, then this should be also proportional to the helicity charge carried by its U1 hypergauge field. So in this way, because of this chiral plasma instability, you are generating some asymmetry in the standard model sector, and at the same time, you are generating some range configuration in the U1 hypergauge field. But this is, unfortunately, this is not the end of the story. Suppose this happens, then what is out? Okay, let's just suppose that this happens at this temperature, and you generate BB dual, non-vanishing BB dual, and right-handed electron in this way. But however, after electroequivalent conditions, then the electron Yukawa becomes efficient. Then this electron Yukawa is the asymmetry in the electron, right-hand electron would be immediately washed out, because once the electron Yukawa comes into equilibrium. But however, that something that is carried by this BB dual is still there. So that is the important outcome of this mechanism. So we have HY is defined so that total derivative of HY becomes an integral with some factor. This is non-zero. And at electrolytic condition, what would happen is the conversion of this helicity, helical, sometimes which is called, it is referred to as helical charge of this U1 hypergauge field to helical charge of the electromagnetic. So this is the horizontal axis is the helical charge of the electromagnetic, and the vertical axis is the helical charge of U1 hyper. Yes.
Can I ask the question? So the BV dual, the production, which modes are being produced? Are they like with K or to the temperature? Or?
Good question. So essentially this is determined by this this one. So this is essentially some factor times μi5. So for given μi5, mode who has the smaller wavelength than this μi5 should be generated.
I see. Okay. So can you hope to see this in something like gravitational waves from this or something like that? If the mu is small enough so that the K are close to horizon scale? Or...
I think the scale is too small for the typical gravitational wave detectors.
You mean just because the temperature is high? This happens early on?
Early on, and also the mu is a bit suppressed by the temperature, but still it's high. Because but this effect should happen before 10 to the 5 GeV. So it's super high temperature. And
I mean, not for
not
gravity
that
waves.
high.
Not for gravity waves. No?
Yeah.
Yeah, right.
LIGO range, no? Or,
Yeah, right.
Yeah, it's
even,
below light.
light
is even higher.
Yeah.
Yeah, it's below light. I think it's
This is like the Einstein telescope.
The side or
the side, what is the side?
The side,
Yeah.
I think we have discussed that already. I just forget to.
No, but maybe mu is just too large.
No, mu should be of the order of. Right, so in order to have this effect at this temperature, so mu should be, say, larger than 10 to, sorry, mu divided by temperature should be larger than 10 to minus 3 or something.
Oh, I see.
So, sorry, yeah, maybe it's too large. Yeah.
You see.
In comparison to that word, it's, and if this mu is smaller than this, then we don't have instability because because the efficiency of this growth is also characterized by the magnitude of mu. So, if you complete the square, then it will be something like something square plus.
But isn't it comparable to Hubble? Don't you need to compare it to Hubble to get the efficiency? I mean, the instability is there, no? If you have
yes, we have to compare it with Hubble, and I don't explain anything, but this is the conformal term, and
I understand.
Yeah, it's already taken into account. And if you assume that this should happen within
so that's why
above this temperature, then you get some constraint of mu. Yeah, I should have written here. So this mu over t should be larger than 10 to the minus 3.
What is TC? What is that for the what? Right, sorry, what is this?
This one.
No, the big T, the first one.
Temperature. Sorry.
No, the first.
Fast T. This one.
Yeah.
Sorry. This one is the when this happens for given mu. Sorry.
When what happens? The instability.
The instability, the instability occurs.
The production.
The production of gauge field from the non-vanishing mu5. So for given mu5, we can estimate when this happens, and this is the temperature is estimated in this way.
Where is the 10 to the minus 3 coming from? I mean, why is this
Why is this value? I don't know. I just normalize these things to really close to 10 to the 5 GB. Then I somehow get 10 to the minus 3, but I don't know.
I see.
Probably just a numeric stuff. Yeah, so sorry, I skipped this explanation. So at this temperature, this gauge field production occurs, but we want to have this gauge. In order to have this effect from lepton flavor asymmetry, then this TTPI should be larger than 10 to the 5 dB. Otherwise, this chemical potential that drives this instability vanishes because the right-handed electron recover becomes efficient. So this puts the lower bound onto the magnitude of mu5 divided by temperature. So we typically need the chemical potential of the order of 10 to minus 3 to have this effect. So I'm probably running out of time. At the electric phase, so let me just repeat the same thing. And so suppose that this happens, and mu5 divided by temperature is larger than 10 to the minus 3. Suppose that this, then you get the non-vanishing magnetic field, and at the same time, non-vanishing right-handed electron symmetry. But after temperature becomes more than 10 to the 5 GB, right-handed electron symmetry is washed out because the right-handed electron becomes efficient. But still, the magnetic field is there, and they persist until electric phase transition and decays. Yeah. And this decay of the helicity sources the production of the baryon asymmetry in the end. I just skip the details. We have some terms like washout coming from spiron, and also some terms which is essentially coming from the effect of dB dual. I don't write down the complicated expression, but these terms becomes non-zero at the electrical equation. So because the U1 hyperhelicity is now going to be 0 because they are converted to the helicity of the U1 electromagnetic. So essentially HY is decaying. If HY is decaying, this is proportional to, by construction, this is proportional to the total derivative of HY, so this is non-zero. So this is also non-zero. So it means that you are sourcing, you have a source term coming from the dynamics of this U1 hyperhelical field. But of course, Baryon tries to wash out everything. So the competition determines the final outcome. And so it should be given like washout factor times something. If something is just coming from the definition of HY, so you can just forget about it. But HY divided by entropy density. Produced by theoretical activity. So you can see that the some amount of, if you have spherical magnetic field before electric phase transition, you can generate the baryon asymmetry some amount. But typically, you can show that, okay, so this is the washout factor coming from the spiral, but actually this dynamic is super complicated at the electric crossover. So we have huge uncertainty here, but the typical value would be 0.05 of the order 10 to minus 3, but in some estimation, this can be as small as 10 to minus 6. So there are huge uncertainty here, but let's just take this value. Then you will find that this one is too large. And that is coming from the conclusion, the effect that because typical value of H divided by S produced by this mechanism is too large, then typically you overproduce the baryon. The reason why we get large H helical charge is simply because we need to generate helical charge before at the temperature which is greater than 10 to 5 GP because of this restriction. So for this reason, H divided by S is super large, and then you overproduce baryon. So in the other way around, if you have very large lepton flavor symmetry, you overproduce the baryon symmetry. Just write down final expression. So this is it. So you can see that if you have this 3 over T of 0 of 10 to minus 3, you overproduce baryon. For this choice of the conversion factor. But as I said, maybe it can be a small 10 to minus 6, then it is a good value. That's all. Anyway. Yeah, and this puts the upper bound of the lepton flavor symmetry. And as far as I know, I think this is the tightest upper bounds of the lepton flavor symmetry. I mean, primordial lepton flavor symmetry that exists.
Sorry, upper bound assuming
upper bound,
epsilon, yeah?
Sorry?
Upper bound.
Sorry, because if you have UI5 greater than 10 to minus 3, we have this chiral plasma instability, then you get this value. This is too large, so, but it should be smaller than 10 to minus.
Again, what is this epsilon? Remind me again. What is it?
So if you have, suppose that you have the lepton flavor symmetry, and if you have large enough lepton asymmetry of the order of rather than 10 to minus third, then you have chiral plasma instability in the other universe, and then you generate magnetic field and asymmetry in the right-hand electron. But right-hand electron asymmetry is washed out after the temperature becomes smaller than 10 to minus 5 because the electron recovery becomes efficient, but still magnetic field remains. And they persist until electric phase transition. And then at the electroweak phase transition, the even hypermagnetic field decays, and that decay shows the total baryon asymmetry.
And again, this epsilon is just coming from this equation. I mean, I'm just trying to understand where.
Sorry. This epsilon is just coming from the Spartan motion.
Right.
Yeah.
Okay.
Sorry, I'm confused just by something. So this magnetic field
supported
by some current, no?
Magnetic field is supported by magnetic.
But then the current is washed out because you don't have any more. Once the electron Yukawa gets at equilibrium, you lose this.
You don't have asymmetry, but the current is zero. And another thing I skipped is that the system becomes into the turbulent regime. So it means that the magnetic flux becomes initially the magnetic flux is how can I phrase this? But it is known in the MHC numerical simulation that if the system enters into turbulent regime, it means that the system has the large coherent magnetic field.
Yeah, so that's what I was hinting to. So these magnetic fields are somehow more long-lived than what generate them.
Yeah.
And do you have like some?
And if you have,
do you know why? Like, do you understand why?
Typically, the dynamics of the plasma try to disentangle the how can I say this? The complicated structure of the magnetic field flux. Then as time goes, the typical magnetic field mode that dominates this magnetic field velocity is carried by long wavelength magnetic field. So it's like the domain wall network. In the domain wall network, you have the one domain wall per happle because they are collapse but The typical one is dominated by the largest one, right? So in this way, the typical helicity of the magnetic field is somehow carried by the large wavelength magnetic field. Then they can escape from the diffusion because diffusion happens in the small scale, but they cannot catch up this diffusion. And that condition is essentially one of the conditions to have turbulence. But I cannot say more about this. And if this happens, then the helicity of the magnetic field becomes an approximately conserved quantity. And if you have approximately conserved quantity in the turbulent regime, you have inverse cascade. It means that this thing charge is dominated by a long wavelength. So typically we are going to UV and UV.
So but you need to enter this regime such that this magnetic field becomes essentially long-lived up to this decay.
Yes.
Because otherwise they would just
right. We just have diffusion and diffusion.
Yeah,
created everything. Yes. Right. So and that discussion, essentially, to have the long-lived magnetic field, you have to impose the condition to have turbulence. Well, Reynolds number at the production should be greater than unity. Magnetic Reynolds number and also kinetic Reynolds number. And actually, in this production mechanism, these two conditions are automatically satisfied. You can show that right after production, Reynolds number are very, very huge. And we expect that the system goes into the turbulent region. But we don't show it because we need some numerical solution.
Can you dilute it like with non-standard, say, secondary short phase of inflation at this temperature after production? I mean, can you evade this limit that you just mentioned on the by non-standard cosmology, simple non-standard cosmology?
Yeah, of course you can. If you dilute, then you're fine.
Yeah, because it happens at late time.
Right.
I mean, at relative high temperature, late times are still relative high temperature.
Yeah, right. Okay, that's it. So, thank you.
We had lots of questions, but if anyone wants to ask something more, we have time. The cafeteria opens at 1, so. Yeah, okay. So then, thanks a lot. Thank you.